Hi guys, this is a video for basic fundamentals of Laplace transform.
Okay, now, so Laplace transform basically takes in a signal in a time domain. So here I will denote the function of a signal by using a small letter f, okay? And it is actually a process, yeah? The Laplace transform is actually a process that transforms the input signal in time domain and convert it into another signal in the spatial domain. So I just would like to highlight here is in order to differentiate the two signals, for the one in time domain, we use the small letter f for the function, and the one for the spatial domain, we use the capital letter of f to indicate it is a function in the spatial domain. So basically, the formula for Laplace transform is a function in the spatial domain, which is the output of the Laplace transform, is an integration from 0 to infinity. Again, if you have an integral, you have at the end dt. Yeah. So your input here, which is the function in the time domain, needs to be multiplied with a kernel function, which is an exponential to the power of negative st. All right, okay. So basically, a Laplace transform here utilizes a kernel function. So exponential to the power of negative st is a kernel function, which is in the form of exponential decay. So the beauty about exponential decay is that when you substitute the value of 0 to infinity, either 0 or infinity, if you substitute the value inside it, it will give you some output, some definite results. All right. This let me just demonstrate you here. This is an example of exponential decay, e to the power of minus t. Let's say we take the general exponential decay function. So when t is at time 0, the exponential decay will cut the y-axis at 1. And as t is approaching infinity, the exponential decay function will actually goes towards 0. Yeah. So I will demonstrate this later with an example. Let's go to example 1. Yeah. Assuming you have a signal which is static in the time domain at 1. Okay. So your function in the time domain ft is equivalent to 1. Now, your fs, which is the function in the spatial domain, we will apply Laplace transform, which is an integral function from 0 to infinity. We take in the input signal itself, which is 1, multiply with a kernel function, which is exponential to the power of minus st, and don't forget your dt here. The answer to this will be exponential to the power of minus st over minus s, and the whole thing must vary between the limits, which is from 0 to infinity. Okay, so when we try to substitute this value, let's substitute it first. Exponential to the power of minus s, first we substitute the value infinity. We minus with exponential to the power of minus s, we substitute the next limit, which is 0. Okay, and don't forget it must be over minus s. So if you realize this, coming back to the exponential decay function, when it is at infinity, it is actually 0. And when it is at time 0, it is actually 1. So we can substitute the value here. Let's try to solve this. So you will get 0 minus 1 over negative s, and we can cancel off basically the negative from both sides, top and bottom, and you will get an answer of 1 over s. Okay, it's as simple as that. Okay, now let's go to the next example, something which is slightly more complicated. Assuming you have an input signal which is exponential to the power of at. Now here a itself is a constant, okay? It can be any value, 1, 2, 3, doesn't matter. Let's assume a is a constant. So your Laplace transform in the spatial domain, again, it is an integral function from 0 to infinity. You take in your input signal, which is exponential to the power of at, multiply with the kernel function, which is exponential to the power of minus st. Okay, and let's try to solve this, since this is a multiplication function, so you can combine both exponential at plus with minus st, and this is dt. Bear in mind, we want to make sure that this is in the form of negative exponential function. Let's try to modify this. We want to make sure that this is in the form of exponential decay function. So exponential decay, you will have negative here, you will have t here, and inside it, in this case, we will have what we call it as s. So negative here, you will get negative s minus a. Okay, so this is your function in the form of exponential decay, and you will get the result, which is exponential to the power of minus in bracket s minus a times with t over s minus a in bracket, don't forget your negative here, and it should vary from the limits, which is from 0 to infinity. Now let's just substitute the value. Exponential negative s minus a in bracket, that is varies from infinity, okay, minus with exponential negative in bracket s minus a, the next limit, which is 0, and all of it is divided by negative in bracket s minus a. So here we can substitute the values. You know, where it is at infinity, it will be 0, and when it is at 0, it will be 1. So the result of this will be negative 1 over negative in bracket s minus a, and we can cancel off the negative of both sides, top and bottom, and your final answer will be 1 over s minus a. So it is as simple as that. Okay, now the two examples which I have shown you basically corresponds to the Laplace transform here. So the first one is this part, yeah, which is given an input 1, your Laplace result will be 1 over s. The second one is here, given an input exponential to the power of at, the result will be 1 over s minus a. Okay, for the next subsequent examples, I will use this Laplace transform table directly. That's it for this video. Thank you.